This is a lecture on the bell-shaped curve, also called the normal distribution or the Gaussian distribution. What I'm presenting here isn't discussed directly in the Mendenhall text, but there's some very useful rules of thumb here. The shape of the bell-shaped curve is totally determined by the mean and the standard deviation of the data. Okay, so it determines the shape. It also gives you the equation for the curve. That's all you need to draw the curve. And there's also certain important areas under the curve that you can find just by knowing those values. So here, example of 3 of these Gaussian distributions or bell-shaped curves. Remember that what is given here is the probability density, not the probability itself. So here's the mean. The mean is right in the center of the curve. And in this case, all 3 have the same mean, but they have different standard deviations. And you can see how that determines the curve. Notice also that the peak of the curve changes with the standard deviation. The reason for that is that these are probability densities, right? And the probability is the area under the curve. So if you have the case here, like for this curve with a standard deviation of 30, you've got the higher tails out here. That means there's more area out in the tail section for that one than there is, here's sigma of 30, than there is for a standard deviation of 10. So because there's more area out here, this peak has to come down so that the total area under the curve, okay, the total area, I'll just write it like that. It's tempting to write it in using integral, is 1. And that's why that peak comes down. So you see the height of this changes, not because the mean changes. The mean is only the location. That's a location here, and this is a probability density. Here's the equation for that bell-shaped curve. It looks a little complicated, so I'm going to look at it piece by piece. So what we're looking at is the probability density, which I'll just write as F, of some arbitrary data value y. And there's a normalizing factor out front, which is 1 over the standard deviation times the square root of 2 pi. I'll just put that out front now. Then we have E, Euler's number. E is related to natural log, and all of these other values that I'm going to give here are the exponent. They don't multiply E, they're the exponent. It's negative exponent y minus the mean squared divided by 2 times the standard deviation squared. Remember, that's entirely the exponent. So for that red curve in the previous graph, the mean was 100. So the 100 goes right there. Remember, inside that parentheses, and the standard deviation was 10, so we see it 10 here, and we also see that 10 down here. Certain areas under this curve are known. These are approximate areas. This is just approximate, but like I said, it's good rules of thumb. Okay, so here is our setup. The mean is in the center, and now if I move up 1 standard deviation or down 1 standard deviation, the area right in through here is 34%. That represents the probability that a data value will lie between these 2 values. So what's a what's a probability that, probability that data value lies between those 2 values, lies in this area, is 34%. What's the probability it lies between 1 and 2 standard deviations, either above the mean or below the mean? 13.6%. So if you want the probability that it lies in this area, plus and minus 1 standard deviation away, that's about 68%. And this holds for all normal distribution curves. Of course, everything that has kind of a bump in the middle of it isn't a normal distribution. To be a normal distribution, it has to follow that formula that was on that equation that was on the previous slide. So here's an example of just an example that I'll use in this slide and in the next one. So you had a study, and in that study you found that for the people that you studied, the mean systolic blood pressure was 20, and there was a standard deviation of 10. So this curve could be drawn like this. You've now not including all the data values at all. Okay, you're saying that this is the probability density for this curve because it's normally distributed. There will be another lecture to determine whether the data really is normally distributed, but say it is, and then here is your probability density associated with a mean of 120 and standard deviation of 10. If you want to know the probability that a systolic blood pressure lies between 120 and 130, that would be between the mean, because 120 is the mean, and this is the mean plus 1 standard deviation. This area is known as 34%. And here you'd be looking at the probability that the blood pressure was between the mean plus sigma and the mean plus 2 sigma, and that'd be 13.6%. So here you can see how you can use these known areas under the curve to compute the probability between different values or different values of standard deviation away from the mean. This would be, here's your mean, and our standard deviation is still 10, so this would be 2 standard deviations above to 2 standard deviations below the mean, and the probability that the blood pressure would lie between 2 standard deviations above to 2 standard deviations below the mean is the sum of all these areas that we know, and that's 95% approximately. Here are some more facts to remember about this bell-shaped curve. Again, when I'm saying bell-shaped, I mean the normal distribution, also called the Gaussian distribution, and it is a curve that follows that equation that I showed you earlier. Okay, for that bell-shaped curve, normal distribution, the mean, the median, and the mode are all in the same place, right in the middle of the data. Okay, right in the middle of the curve. I'm sorry. The curve is symmetric about the mean, so right and left sides are the same. Okay, and the total area under the curve is 1, or you could say 100%. Remember, the area under the curve represents the probability because the curve itself is probability density, so the area is probability, and the probabilities that any value will occur is 1. Probability is the maximum probability is 1, so that is the area under the curve, and that can be used, and that is used in finding probabilities for values that do not fall exactly on the mean, or 1, 2, 3, or 4 standard deviations away from the mean.